Okay, now we start the section 2.1. Chapter 2, Linear System of Equations. And the linear system of equations and its solution is one of the most important problems in linear algebra, which has lots of applications in all areas of science, including science, engineering, and social science, and medicals, and all things, all areas of the sciences. Even differential equations concerning derivatives such as velocity and acceleration can be solved by transforming them into a linear system of equations. In linear algebra, a solution of a linear system is obtained by Gaussian elimination method, or with determinant. In this chapter, we consider a geometric meaning of the solution of a linear system and its solutions, and investigate some applications of the linear system of equations. I added those who made a great contributions in this area of mathematics. Okay, yeah. In this chapter, yeah, we consider geometric meaning and relations between a linear system of equations and its solutions. Okay. Section 2.1. Okay. You may go into the lecture that I gave a couple of months ago, which has been recorded.
해결하는 선형
which has many interesting features.
호모지니어스 시스템 오브 리니어 미지수와 시계수가 모두
that you can find in here. This is in Korean, but yeah, from here you can see the definition of the linear system of equation and its solutions, and here are some examples, and here are some problems and also solutions, and the problems and solution with the computational tools as well. If you change it, the problems or conditions, then you will have different answers, like you see. So you don't have to memorize all the command of Sage or Python to do all these computations. Anyway, I have added those web addresses that you can utilize it. Okay, here, section 2.1. A theory of linear system of equations is the basis and the fundamental part of linear algebra. Okay. Computational algorithms for finding solutions are an important part of a numerical linear algebra and play a prominent role in engineering, physics, chemistry, computer science, and economics. In this section, we study the process of finding solutions of linear system of equations and its geometric meanings. First definition is about the linear equations. We call this type of equation is called the linear equation, which has scalar times variables. It may have many variables, and add the combination of those. Actually, linear combination of n unknowns is equal to a scalar. Then we call this is a linear equation. This part is a linear combination of the variables or unknowns. Okay. That's why we call it the linear equations. In other words, a linear equation consists of variables of degree 1 and a constant b, like this. These are the examples of linear equation, and these are the examples which are not linear equations. Linear system of equation. In general, a set of m linear equations with unknowns, x1, x2 to xn, is called a system of linear equations. This type, this one set of equations like this is called a system of linear equations. If these coefficients b1, b2, and bm's are all zeros, then it is called a homogeneous system of linear equations. And solutions of linear equation system. Suppose unknowns x1 up to xn is in a linear system are substituted by SIs respectively, and each equations are satisfied. Then this SIs is called a solution of a linear system. For example, in this case, if we substitute xi's as 1, 2, minus 1, then it satisfies both of these equations. Then we call this 1, 2, minus 1 is a solution. In general, if there is a set of a solution of a linear system, then it is called the system is called consistent, and is called inconsistent otherwise. If we have a system of linear equation which has no solution, we call that linear system of equation is inconsistent. Okay, the set of all solutions of a linear system is called a solution set. And two linear systems with the same solution set are called equivalent. Okay, equivalent. Okay, here are some visual examples of the cases. A given linear system satisfies one and only one of the following. A given linear system may have either has a unique solution like this, or infinite many solutions like this. It's overlap. Same equations. Basically, these two equations represent the same lines. So like this. It has infinite many solutions. Or no solutions like this. It's parallel, then it has no solutions. There are only three cases, and they are all. There is no other cases for the linear system of equation of two variables. And here is a computer simulation that you have made, that you made to practice. Okay, and there are more visual tools of linear algebra in this web address that we have developed. Now, example 2 describes all the case for the linear system of equations with three variables. Suppose we have a linear system of equations with three equations and three unknowns like this. Then let's describe all possible solution sets in R3. Here, we may have a unique solution like this. If those three planes meet at one point like this. If we describe the three different planes like this, then you see there's only one point that all planes meet. And there are also several examples that has infinite many solutions like this. We may have infinite many solutions like this, as a one line overlap, and there is one line and two planes are overlapped, and even all three planes are coincidence like this. All these cases has infinite many solutions. And there are also cases which the system is inconsistent. And that means it has no solutions like this. In this case, and this case, and this case, they do not have a solution. But eventually, there are only, these 8 cases are the all cases that we can describe as a potential solution set in R3. But we can categorize all those 8 cases in 3 categories. One, it has a unique solution, one case. When the case that has infinite many solutions, which is just 3 cases like this. And the last category is the case of inconsistent, which has 4 different cases in R3 like this. The important thing is that we can categorize the 3 cases of the solution set in R3 like what we did in R2. Same thing works for the solution set in R4 or R5 or R10. So if there are only the case for the solution, possible solution set cases is unique solution or infinite solution, at last no solution. That's the only 3 big categories for the solution set. Okay, example 3. Solve the following linear system. Okay, here. You know how to solve it. Here we have 3 equations and 5 unknowns. So usually we assign to any 2 unknowns arbitrary real numbers. Let's say it's S and T for x2 and x5. Then all others, x1, x3, x4, can be written as by using these 2 real numbers. And so x1, x2, x3, x4, x5 can be written in this form with 2 scalars. So so the solution set is all possible vectors of this with 2 real numbers, arbitrarily chosen. So in this case, we can tell this system has infinite many solutions. Here's a matrix, definition of matrix. An array consisting of real number is called a matrix, and each number is called an entry, like this. Row and columns. The row of matrix is called this row. This row is called the ith row of A, and this column is called the jth column of A. A1j, A2j, AMJ, which is in the jth position here. A matrix with m rows and n columns is called a size m by n matrix, and if m is equal to n, it is called a square matrix of order n. And this denotes the ith row of A, and this denotes the jth column of A. Therefore, A can be written as a set of columns and set of rows, set of rows and set of columns like this. We can simply describe the matrix in this form. And the entry ij of a matrix A is called the ijth entry of A, and the entry A11, A22 up to ANN of a matrix of order n are called the main diagonal entries. And the matrix A can be written as the ij entries as follows here. So this A is a m by n matrix whose ij's entry can be written in this way. So here, this A, B, C, D, E, F, this matrix is we can tell the size of matrix and what's the entries of those matrices. Coefficient matrix and argument matrix of a linear system. Okay, suppose we have this linear system of equation like this, then if we let A as a matrix like this and X and B as a vector like that, then this linear system of equation can be written in this form. AX is equal to V, and with this, here we call this A is a coefficient matrix, and this matrix is an augmented matrix of that equation, 3. Suppose we have a matrix like the linear system of equation like this, then A, X, B can be written in this way, and this system can be written in this way, or this way, and augment matrix can be found in this way. This matrix with this B vector at the end. This code gives us how to produce the augment matrices from the given matrix and vector. I think that will do it for that. So, for example, here, if we have a matrix and vector, then the augmented matrix can be found in this way. If we change the matrix, then we will have a different augmented matrix. Okay, in section 2.2, we will learn how to solve this linear system of equation by using this augmented matrix. Okay, any questions for section 2.1?